The talk I'm going to provide is not super high level. I'm going to show you some of the results that we've achieved over the past 25 years or so by looking at pedestrians and bicycles. So in a way, I took the title of the conference quite literal, and I'm looking at one of the oldest means of transportation from a traffic engineering point of view. So, and why, you might wonder? Well, obviously, and I will say a few words about that from an engineering perspective or from a planning perspective. The active mode, as we call it, is super important, right? But as a scientist and as a modeler, I find it super fascinating. I was making the remark about sumo, and with good reasons. This is a typical morning in Amsterdam, and it shows you how super complex active mode traffic operations are, right?
Who is me?
Did you cycle there, Derek? Not sure. Who spots the pigeon? I'm not sure if that's an active mode, but one will pass the street later. Ah, here it goes. Anyway, the only reason I'm showing you this is actually showing you complexity, right? Getting this in models is super involved, and personally one of the challenges for a modeler. So this is really one thing that I found always very inspiring, and well, actually, well, also something that hasn't, in my view, deserved enough attention. There's not so many researchers that really have looked into the modeling of traffic flows of the active modes yet in a very detailed fashion. Dirk has done a lot of work, obviously, but especially on bicycle traffic, there's not so much. I changed my title a bit, right? I've put future in quotation marks and remove them with data because I will mostly be talking about the data challenges that we have. Also because I believe that one of the reasons why the field has not, I would say, went to so many breakthroughs is the fact that data has been lacking substantially. And data is important. High quality data is important. This is the only interactive moment I have. So please bear with me. Very simple statistic, has nothing to do with traffic operations in itself, but it does show the importance of high quality data. Two pictures. Let's first focus on the left one. It shows you, and the print is a bit small, so apologies for that, different age groups, and it shows different BMI levels. So low BMI, that's healthy, overweight, which is between 25 and 30, and obese, which is larger than 30. That is what it shows on the x-axis. On the y-axis, it shows the percentage of people that own a bike. This is Dutch data, so the numbers are pretty high. So let's now first look on the left one. What you can see is that actually for most of the age categories, there's a negative correlation, which means that when your BMI goes up, I'm not going to ask you in which category I am, but if the BMI goes up, the ownership of a bicycle goes down, or the other way around, right? If the bicycle ownership goes up, your BMI goes down. So this is my proposition, right? Cycling increases health. Who agrees? By default, the rest doesn't agree. I'm not sure if you would cycle here if I would, but okay.
Accident statistics should be considered too.
Fair enough, fair enough. But this is just for the BMI level, so. I think it's a 50-50 thing, right?
There's absentee ballots.
Sorry?
There's people that don't vote.
So who
Yes.
Because you're wrong. And you're wrong because if you look, I'll get to that later on. You're wrong because of the data that I showed you, right? It shows a correlation. It doesn't show causal relation between the different things. So what we did is we collected much more detailed data, a longitudinal panel that we've been doing for over 5 years. By the way, it still runs. And we tried to identify the changes in BMI and the changes in bike ownership, and then, well, looked for a causal relationship. And to be honest, the result was quite striking, because what we found is that if a person has a lower BMI, he tends to cycle more, which makes sense. The other causal relation we could not find from the data, right? So when people cycle more, the BMI doesn't necessarily go down over the years. Not sure what that entails. Not sure if there's bike activists here, but something to keep in the back of your head. Now look at the other one. And again, I'm not going to answer the question whether or not I own an e-bike, but here we see another correlation. There's a positive correlation, right? So we see that if the BMI level goes up, it's positively correlated by the ownership of an e-bike. Then the proposition becomes, well, e-cycling reduces health. Is that then true? Well, again, during the same time of data collection and data analysis, it's actually not, right? We could not find any causal relation between the BMI level and the use of an e-bike, or the other way around. There's much more involved and complex interactions there that we need to consider to truly understand what we just saw on the graph. Why am I showing you this? Not so much because I will be talking about it anymore in the remainder of the talk. It shows how important data is to really understand traffic and travel behavior of the active modes. A field which has been data poor, I can say. So this is why we started actually already quite some years ago, an ERC advanced grant project called Allegro, which had as the main idea, let's see if we can advance traffic and transportation theory for active modes by collecting high fidelity data in different ways. Now, I don't have the time, although I try to bribe Dirk with some chocolates. I don't have the time to go into all the details. It was his birthday. Of the Allegro project and all the outcomes. I will very quickly show you what type of data we collected. And this is by now almost 8 to 10 years ago. And the longitudinal panels I was talking about, field observations, VR to study the behavior of people in buildings, route choice behaviors, etc., etc. And we did a lot of controlled experiments. And this is the one thing I want to kind of highlight and say a few more words about. Again, bicycle data is not that omnipresent, right? So we decided to collect very detailed data sets of bicycle interactions. We did about 25 experiments with crossings, with bottlenecks, with weaving areas, God knows what, to really try and identify how people actually behave. One of the things that we were able to do using these data was develop a microscopic model. That's, again, I was asking about UMO, because there's better bottles around than this. Our weapon of choice in this case is always game theory. So we decided to develop a game theoretical model based on the concept of the effort minimizing cyclist that is interacting with the other cyclists. Now, I'm not going to go into too much detail about all the equations. Again, I'm trying to keep a bit high level in this case. But it turned out that we were able to develop a microscopic model based on these game theoretical principles that capture the main phenomena that we saw on the data. Right? All the self-organized phenomena, et cetera, that we see in these type of processes. So in that sense, it was successful. What is also interesting is that we've applied the same modeling framework to pedestrians, but also to mixed flows. And if you look at it then very carefully, you can actually see that it generalizes you're trying to follow me or not. Oh, sorry, I will stand still. I'm always walking around. It generalizes many of the well-known models that we have. The pedestrian model, for instance, generalizes the social forces model of Dirk, right? Which has as a benefit that it also kind of inherits all of the self-organized properties of that model, right? And again, if you're into pedestrian flow modeling, you know that there's very, very efficient self-organization phenomena that we see in pedestrian flow. And that also brings me to a very short intermezzo, because if you know that this type of modeling can be used for the microscopic modeling of pedestrian and bicycle flows, and you see very efficient self-organization, then this framework potentially can also be used to model other type of phenomena, like lane control-free CAVs, or connected and autonomous vehicles, or drones, right? And what's funny, if you do it like this, you can come up with decentralized schemes, for instance, for drones, And you get, again, all these fantastic self-organized, efficient phenomena that we see in the pedestrian flow, but then in 3D. So we can actually learn something from the active mode as well if you start thinking about controlling other types of traffic. Okay, sorry. Back to the experiments. We talked a bit, and Dirk made a good remark about capacities. For bicycles, we actually don't know so much. There's some rough guidelines, but if you really look into the empirical studies that says something about the capacity of a bicycle lane, there's not so much around. So we used our experiments and carefully analyzed that. And you come up with these very simple engineering equations that express the capacity of a road in the width of the road, right? The microscopic processes underlying that very simple equation are quite involved. We'll not go into detail, but it does look something like this, right? So the capacity as a function of the width, W. It's in terms of capacity, by the way, quite similar to a pedestrian flow. And you will see that it's about 8 times higher than that of one lane of car traffic. 8 times. Just imagine what that means for throughput, right? There's a huge difference between how many pedestrians per hour or how many bicycles per hour a bicycle lane can carry versus a road in a freeway. Something important to notice. This is so the width is the width of the lane, and it's not for an intersection. So if you start controlling traffic, it's going to be different, obviously. Yeah. What we also found, and that was also quite interesting, is that like in car traffic and like in pedestrian traffic, bicycle traffic has a capacity drop. So once you run into this intersection and a queue occurs, then the capacity downstream of this intersection reduces with about 23%. Again, highlighting the importance of collecting high-quality data to really start understanding what's going on. This is unidirectional. Yeah, we have other experiments, but again, limited time. I didn't get the half an hour extra. So that's just capacity, right? But the differences in the spatial impact, as we all know, between pedestrians, cars, and bicycles is also huge, right? And these are very well-known pictures. I think many of you have seen them, that showcases the differences between the spatial impact. You see them on the bottom, on the one hand, per different, for the different modes of traffic that we can find in a city. And the differences are huge, right? So you can actually think of, okay, is a car not taking up too much space of our city? Well, the spatial footprint of a pedestrian or a bicycle is so much lower. Again, something that you might already have seen before, but an important thing to keep in the back of your head. Now, one final thing, and then we start going into a slightly different direction. Also relates to this spatial impact, sorry. And it has to do what happens on a network scale, right? This is a bit of a difficult picture where on the one hand, you see the population of a city, and it's a log scale, so be careful with that. And the number of kilometers of infrastructure that we have in the city for different modes of transport. What this shows is how the network size per mode of transport, so cars, bicycles, public transport, how that scales if the population of a city becomes larger. What's interesting from this picture is that all these networks, except for the metro network, by the way, scale sublinear. So that means that larger cities are more efficient, quote unquote, in terms of the amount of infrastructure that they have to cater for all the mobility that you see there. What you also see is that a bicycle infrastructure, a bicycle network, scales much more efficiently than the car network. At least there's a correlation there. Well, let you think of what it means, but it's an interesting thought to keep in the back of your head.
Are the cyclists not also using the car road sometimes?
Sometimes it's so. These are all different cities. It's.
Sorry, just showing the unwillingness of the car drivers to let cycle facilities built.
Sometimes, but not always. It kind of depends on these are different cities worldwide. That was actually precisely the point why the question mark was there, Kai. Thank you for already answering the question. Okay, so my claim here is that we're talking about smart societies. We have the tendency, if we talk about smart, to think about autonomous vehicles and connected stuff, et cetera, If you look at the spatial impact and the ecological impact of the active modes, you might want to also sometimes steer away a bit from the shiny things and making cities more sustainable, healthier, and inclusive in other means than just applying technology. That's not to say that for bicycles and pedestrians, we cannot improve a lot by innovation, right? In Delft, we are doing quite a couple of things to ensure that cyclists are a bit more safe, without a helmet, even try to stabilize bicycles, improve traffic control, for instance, by connected systems, prioritize parts of the network where cyclists and pedestrians actually need priority. And especially in my group, we are looking a lot to data because, as I said before, this is a field that is data poor and sometimes assumption rich. So these are just a couple of examples of our digital twin environment. There seems to be a topic there because many people are talking about digital twins. In our case, we are equipping the campus with all types of innovative sensors and data collection systems to really get a better idea of what happens on the campus in terms of its active mode mobility. And the other thing is the use of VR, which you also have discussed a bit. Okay, so what are active mode shiny things in this respect? What type of innovations are we looking at? Like I said, we're investing a lot in data collection, and I actually like this example a lot. This is in front of the civil engineering building, so much safer than Leeuwarden, André, where we've implemented so-called plastic roads. It's a circular bit of bicycle road. It's made of plastic, recycled plastic. It's also climate adaptive in the sense that it does water containment, but it's also smart. It's smart in the sense that it has many sensors in it that allow us to monitor very carefully pedestrians and cyclists. So this is one of the things that we're trying to achieve, come up with better data collection systems, which can also be used to, well, make data collection a bit more broad than just our campus, right? A bit more ubiquitous. The other thing is that, well, there's some data around. So we have people driving around with apps on their phones that are collecting some data. We have here and there the occasional smart sensor in the Dutch traffic system that collects data on the pedestrians. So can we make something more out of these data? And since until now we have not been super successful in applying traditional techniques, also we have been looking at AI. Like everybody nowadays, I get the idea, to see if we can kind of combine the different data sources that we have in a better way, that we can start thinking about prediction and forecasting, et cetera, et cetera. So the last bit of my talk will be about just that. So 2 examples of projects that we've been doing that kind of showcase in which direction AI can take the improvement, the enhancement of the data that we have. And they're not bicycle examples. The example that I'm showing you is based on crowd risk management in Scheveningen. Apologies for that, which is the beach area in and around The Hague. And the idea is we have 2 commonly available data sources. We have mobile phone data, which only pertains to some of the people that carry on a phone with a specific app on it, which obviously is coarse, but it's also biased because you don't have everybody, and especially if you're going to the beach, well, think about that. And the second one is the Google data, the POI data, which is temporarily very coarse and potentially also biased, by the way. The thing that we try to do is see if we can combine these data to see if we can get rid of the bias on the one hand, but also increase the especially temporal resolution of the Google POI data. And that seems to be the case. It seems to be the case that if you apply the right AI technique, and we've done multitask AI for state estimation in this case, you will be able to get rid of some of the bias that we get in either of the data sources. So that's promising. At the same time, I'm managing Dirk. We've also tried to see if we can then use these data from long-term prognoses. And that also turned out to be possible. And that's an important application. First of all, these long-term forecasts have been rather difficult under these circumstances for this type of modeling. And in this case, AI seemed to help. For the users, they're able now to plan the emergency services, et cetera, based on the longer-term plannings that we've been able to derive using AI. But that begs the question, because everything is AI, right? Everybody is doing AI. And in statistics, are there any statisticians here? There's a very common saying, you cannot make a silk purse out of a sow's ear. Well, AI can definitely make a picture of a silk purse out of a sow's ear, sort of. But the question is this really true, right? I mean, or are there still all type of things that we need to solve, domain knowledge that we need to put in? And that's actually something that we're now going to explore in the coming future with our digital twin and all the different projects that we're doing, including the AI Compass we're doing together with Tina. Problems are still there. Data availability is definitely an issue. For many of the applications, we are actually interested in the exceptional situations for which you often don't have data. Are you going to do that? Data is heterogeneous, is noisy, et cetera, et cetera. The system is very complex. That's going to be something that's going to be difficult. The context has a large influence. And finally, there's many other aspects that bear strong relevance for what we're trying to do with AI. And that many of these have to do with ethics and privacy. I'm going to leave you with this and then this statement for our research in the coming 5 years or so.